Welcome back. In the last session, I spoke about figure of merit of RC phase shift oscillator. The first one was the frequency range. It is in the order of 100 kHz, and the second one is there is no frequency stability. I just explained why the RC phase shift oscillator is not able to give you very high frequency of oscillations. That is because of your open loop amplifier bandwidth limitation, right? Because we cannot get gain, which is what 29 for all frequency components or for all frequency range. Therefore, it is limited with the bandwidth. And number two, there is no frequency stability. If there is no frequency stability, the frequency of oscillations will change. Why frequency of oscillations will change? That I'll explain qualitatively. Yes, this is also explaining. If temperature changes, your R changes. If R is changing, your F0 will change. Mathematically also I can explain, but let me explain qualitatively. That will help you to understand the circuit which is a crystal oscillator, how to get highest frequency stability from that, and how are we getting it. Therefore, it is easy to understand qualitatively rather than understanding from quantitative analysis. Okay, that part I will explain. I'm going to explore what is the meaning of frequency stability. Okay, and people defined something called mathematical frequency stability definition. Then we will see that. Okay. And this is the time to explain. I told there is no input. I told noise is the input. Therefore, how the noise is input, I'll explain. This is the time to explain. I told you if I explain everything at the same time, we will not understand. We have to go incremental way. Therefore, I'm explaining what is the meaning of input, or what is the meaning of input is there and then input is not there. That is what I explained. Case 3, B, sub case B. I'll explain now how the noise is acting as an input for your oscillator. Done? I think I gave you sufficient time in the last session, and I told that you have to write down. Done. Let me explain frequency stability. Frequency stability. Actually, this is defined as, therefore, mathematically people defined frequency stability. It should be what? It should be very high. When I say stability, frequency stability is infinity. I can say the resonant frequency is constant. That is not changing. If I say frequency stability is very low, means stability is not less. Stability is not very high. It is low stability, means the frequency of oscillations will change. Therefore, it is defined as 1 by what is the change in the frequency omega due to the change in the loop phase shift, where theta is nothing but or d phi, anything is fine, or d theta. This is what. Now let me explain. Just listen here. Okay, I am explaining. If you consider only for RC phase shift oscillator, right? Let temperature of the circuit, let us say 27 degrees Celsius. Then what is your beta network? Let us say your beta network is giving, this is what your open loop amplifier, this is A, then this is what is your beta network, right? Therefore, if I take beta network, RC, right? Then this output is going and then given to input. This is C, R, right? Therefore, assume that R and C values are chosen such that let the frequency of oscillation F0 is equal to 1 by 2 pi RC root 6 is equal to 1 kilohertz. Okay. Therefore, your beta network is giving 180 degrees phase shift, and your open loop amplifier, this is also giving 180 degrees phase shift. Right? At what? This is giving 180 degrees phase shift at resonant frequency. That is what your resonant frequency, 1 kHz. Okay. Now, typically, I'm just taking typical value. Let us say I'm expecting the phase shift by this RC network. Therefore, this is what is 60 degrees, and this is giving 60 degrees. Now, this is what is giving 60 degrees. At what? At F0, where F0 is equal to 1 kHz. Okay. That is fine. Now, just listen. Therefore, what is the phase shift by one RC network? One RC network phase shift is nothing but what? Let us say RC network phase shift. Therefore, what is the RC network phase shift? That is nothing but phi. Phi is equal to, I told you, right, 90 minus tan inverse omega into R into C. I'm just taking isolated RC network. Okay. Therefore, now tell me, if temperature is increasing, then what will happen? Therefore, this is what is 27 degrees Celsius. Now, temperature is equal to 37 degrees Celsius. Your temperature is increased. If temperature is increased, what will happen? Let us say your R value is increasing. If temperature increases, let us say R is increasing. When R is increasing, then what will happen to your phase shift? Tan inverse omega RC for the same frequency, then what is your tan inverse omega RC? When this is increasing, the phase shift will increase. Tan inverse omega RC will increase. Then 90 minus increase, your phase shift will decrease. Therefore, if temperature increases, let us say, if temperature increases, assume that your R is increasing. When R is increasing, what is your phase shift? 90 minus tan inverse omega RC. Therefore, when R is increasing, your phase shift will decrease, right? What will happen? Whatever 60 degrees you are saying, it will be less than 60 degrees. Let us say this is what is becoming what? This is what is becoming, for your understanding, let me take 58 degrees. This is also becoming 58 degrees. This is also becoming 58 degrees. Due to what? At what? At F0. F0 is equal to 1 kHz. Therefore, now tell me, at F0 is equal to 1 kHz, because of temperature rise, your R is increased. When R is increased, let us say your phase shift is becoming 58 degrees from single RC network. Then tell me, here we are expecting phase shift to be equal to 60 degrees, right? But you know, because of temperature rise and because of R increase, because of that, your phase shift is becoming 58 degrees at F0. Therefore, tell me at F0, which is nothing but 1 kHz, 58, but let us say this is what is giving 180, then tell me what is your overall phase shift by your beta network? It is not 180, it is 174 degrees. Then overall, your 180 degrees is becoming 174 degrees. Therefore, now tell me, this is 174 degrees, this is 180 degrees. Then you tell me, you know what will happen? Now, the total loop phase shift is 354 degrees, not 0 degrees or not 360 degrees. That frequency of oscillation, whatever F0 you told, that will be died out. Because Bar-Khausen criteria, the total loop phase shift must be equal to 0 degrees or multiple of 2 pi to get frequency of oscillations. But now because of temperature and because of phase shift change, the F0 whatever you are assuming or whatever you are expecting or whatever you are trying to get, which is 1 kHz, that will die out. If that is dying out, then you know what will happen? New frequency of oscillation will be generated. What is that new frequency of oscillation? Now, mathematically, if I explain, then I will come back to qualitative part. Therefore, now tell me, your R is increasing. Your R is increasing due to temperature. Then, if omega is decreasing, right? That is what is qualitatively. Therefore, omega, if it is decreasing, to get phase shift always 60 degrees, then how much increment in R, same amount of omega decrement if you have here. Therefore, how much is the increment, same amount of decrement if you have here in this RC phase shift oscillator, then your phase shift will be maintained 60, 60, 60. When I say omega decrement, your F0 decrement, when I say F0 is decreasing, that is indirectly nothing but what? Therefore, if you ask me practically, your omega will increase, means F0 will increase to get phase shift 60 degrees. Therefore, angle of beta is equal to 180 degrees. Therefore, assume that, therefore, let us say new resonant frequency 1.1, it will decrease, right? It will decrease. Decreases. Let us say this is what is 0.95 kilohertz. 0.95 kilohertz. Okay. Therefore, there is a change in the resonant frequency. That is what is F0. Mathematically also I can explain the same thing I explained, right? What is that? If R is increased, your F0 will decrease. Therefore, we are going to get new F0, but whatever F0 you have 1 kHz, that will die out because positive feedback is not satisfied, or restoration is not satisfied, or Barkhausen criteria is not satisfied. That will be completely died out. That will be completely died out. Then it will pick up new frequency component. Now this is the time to explain how it is going to pick up a new frequency component. First of all, how noise is input. That part I'll explain. But everybody understood a little bit about mathematical analysis and qualitative analysis. What I am saying, R is increased, but omega will decrease to get 60 degrees. Therefore, then if it is 60 degrees and then 180 degrees, again at what frequency you get 180 degrees? This is 180 degrees. At what frequency the total loop phase shift is 0 degrees? That will be restored. All remaining frequency components will be died out. Okay, fine. I'll explain why noise is the input and then why the new frequency component is coming into picture, which is what is decreased, and then why 0.95 kHz is restored. That part I will explain. Okay, take it. Therefore, in this example, if you ask me what is the change in the phase shift, the change in the phase shift is 6 degrees. What is the change in the omega or frequency, let us say, which is nothing but 50 Hz. 50 Hz change in the resonant frequency due to 6 degrees change in the phase shift. I just took one example, I am explaining. But practically what I am expecting that the change in the phase shift frequency should be very small. If there is a change in the phase shift, very large. For a large change in the phase shift, I want to see small change in resonant frequency. That is what is nothing but frequency stability. Okay. In the case of RC phase shift oscillator, the change in the frequency is significant even though there is a change in the phase shift by a small value. That's why it doesn't have frequency stability. Okay. That's fine. And not only that, your resistor is function of temperature, I agree, but your resistor is also having tolerance. Tolerance in the sense, just listen, assume that we are doing this experiment in the lab. When we are doing this experiment in the lab, then let us say in the classroom 60 students are there, then each batch is having around 4 students, then 15 batches are there. Everybody is trying to do RC phase shift oscillator. Then everybody is trying to get 1 kHz exactly. Then you are calculating theoretically to get 1 kHz. Then you are choosing R is equal to, let us say 1 kilo ohm. Then you are choosing C value. Let us say you got some C value. Then you are going to lab in charge asking for 3 resistors and 2 resistors for Opamp, 3 resistors for your RC network, beta network, and 3 capacitors. You have taken, you connected, you got output, you are seeing. All 15 batches will not get the same resonant frequency, even though you are asking for same types of resistors and same type of capacitors, but different people will get different resonant frequencies. That is because of tolerance. Even though you are asking for 1 kilo ohm resistor, that is not 1 kilo ohm, that will have plus or minus something. That is what, when you go to lab, because we know color coding system, right? How much is the tolerance? What is the resistance value and what is the tolerance? Is it plus or minus 10%, plus or minus 20%, plus or minus 30%? Therefore, because of which even if you say 1K, 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 it won't be 1K, 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 then what will happen? You'll get different resonant frequency because your R value is not as expected, which is 1K. Different people will have different tolerances. Therefore, to decrease the tolerance or to increase the accuracy of your resistor, it should be costlier. You have to go to market, purchase a new resistor which is having lesser tolerance. It is almost constant except temperature variation. The variation of your resistor from the fabrication that can be decreased by purchasing a quality resistor, but that is costly. Instead of that, you know what people do? Yes, there is a temperature change, there is a tolerance effect, whatever it may be, ultimately I want 1 kHz. Then even you put it, you will not get 1 kHz. Then people will have tuning of capacitors. When you tune the capacitors, you are adjusting C such that whatever may be R value, whatever may be the temperature, ultimately you want to get 1 kHz, therefore you will tune the C for a tuned value of C, then for a value of R, you will get 1 kHz sine wave. That's why people tune the capacitor such that you will get 1 kHz sine wave. If temperature changes again, we have to do tuning to get 1 kHz. Okay. That is the limitation of your RC phase shift oscillator. That's fine. Therefore, it doesn't have stability. That's why even though you have tolerance, even though temperature is changing, yes, there is a change in the phase shift. Even though there is a change in the phase shift significantly, if the change in the frequency is not significant, that is very good, right? That is what you get from crystal oscillator. Even the phase shift is changing significantly. I'm not saying that frequency won't change. Frequency will change, but the change in the frequency with respect to the change in the phase shift should be very small. If the change in the frequency is very small with respect to the change in the significant phase shift, then people say that it has very high frequency stability. That is what we get from crystal oscillator. That is what people use to get highest frequency stability. Now this next thing, how noise is acting as input to get oscillations. Okay, then I'll give you 30 more seconds, try to write, then I'll explain how noise is acting as an input, then I'll give you practical considerations of loop gain, then we can go for next circuit. Okay, what is the figure of merit of RC phase shift oscillator? The frequency range is in the order of 100 kHz and there is no frequency stability. Okay, we are trying to improve those 2 points, and then finally we will get an oscillator. Therefore, it should have very high frequency range of oscillations and it should have highest frequency stability also, right? In this example, maybe you can write, tell me what is the change in the resonant frequency. Change in the resonant frequency is 50 Hz due to change in the phase shift. What is the change in the phase shift? Delta theta, loop phase shift, complete loop phase shift due to change in theta, let us say 6 degrees in this example, right? Therefore, practically what do you want? Even though there is a change in the phase shift, let us say by 20 degrees, if the change in the frequency, let us say 1 Hz, that is better, right? Means the change in the frequency is very less, even though there is a change in the phase shift by a large value. That is what we are trying to get it, right? In this example, that's fine. Now, how noise is acting as input. Just listen, right? Tell me, do you have any external input? There is no external input. But remember, let us say there is a noise which is what is coupled to input of your amplifier. Whatever noise you are giving at the input of your amplifier, right? That noise is having all frequency components, because if you take time domain noise, this is what your time t and this is what is your noise profile. Okay, then the time domain noise will have something like this. Now when I say this is what your thermal noise, let us say I'm just taking thermal noise, right, which is random. Therefore this is thermal noise. I'm just explaining with respect to thermal noise. This is the main source of your noise. thermal noise which is random. If you take this as a process, random process, expected value of that random process due to thermal noise is equal to 0, means the mean value of your noise is 0. Okay, what that may be. And if you calculate the Fourier transform or power spectral density, right, frequency domain, then this is what your frequency, okay, and this is what your power spectral density. Therefore, if you calculate the power spectral density of thermal noise, right, or Gaussian noise or white noise, that's what people say, it is flat. It is flat. What does that mean? If you take double-sided spectrum, then you'll get eta by 2, which is kT by 2. If you take single-sided spectrum, that is nothing but kT. Therefore, what is this? This is what is kT value. I'm just taking single-sided spectrum, 0 to infinity, right? Or if you take double-sided spectrum, you'll get kT by 2, what it may be. Therefore, what it may be, anything is fine, okay? Now you are having something, it is proportional to kT. Therefore, it's not alpha, you may say it is alpha. Okay, this is the value, it is eta by 2, eta, single sided spectrum, okay, which is kT. Okay, now if you take this, what does it mean? Your noise is having all frequency components. Your noise is having all frequency components, means if you add all frequency components, for the strength of each frequency component is nothing but your kT, that depends on Boltzmann constant and the temperature, right? Now let us say at F0, let us say at 1 kHz only, your beta network is having 180 degrees phase shift, right? Therefore, now you know what will happen, there is a noise which is what is coupled. Now let us say only at 1 kHz, only at 1 kHz, which is nothing but your F0, only at 1 kHz, total loop phase shift is equal to 0 degrees or multiple of 2 pi, right? What does it mean? Therefore, if you ask me what is your output, now oscillator output, if you ask me oscillator output, therefore what is oscillator input? This is nothing but oscillator input, this is your oscillator input. Now if you ask me what is oscillator output with respect to time, right, except F0, except 1 kHz frequency component from your noise, if you take all frequency components, for all remaining frequency components except 1 kHz from your noise, right, those frequency components will not have phase shift of 180 or will not have total loop phase shift of 0 degree. Those remaining frequency components will be died out because there is no positive feedback. Only F0 from your noise, whatever noise frequency you have, only from F0, which is 1 kHz, that will have 180 degrees phase shift. That 1 kHz will be restored by your positive feedback, then you will get only one frequency component will be oscillating. If you ask me what is the output, initially your output is also having some noise. When output is having some noise, right, but remember as we go on you will get only 1 kHz sine wave at the output. Therefore, let us say this is what is our 1 kHz, only 1 kHz frequency component is picked up from noise, and all remaining frequency components, all remaining frequency components from noise, and all remaining frequency components will be degenerated, or died out. Therefore, they will not be having negative frequency. Therefore, this is what is our resonant frequency F0. This is what is going to give you F0. I hope everybody understood, right? Now, let me come back. Then, let me tell you a point. Practically, people consider total loop gain greater than 1. What is the reason? There is a reason. If total loop gain is equal to 1, then you know whatever noise you are giving, maybe if you go to case 3, whatever I explained, and then B, input I gave initially, which is 1 volt peak to peak, and then later on I told that input is not there. That 1 volt peak to peak, whatever you are giving initially and then input is not there, scenario, right? Therefore, that 1 volt peak to peak, whatever you are given, that is restored if loop gain is equal to 1. Therefore, whatever you are giving input, which is 1 volt peak to peak, and then leave it, that will be restored. But remember, whatever frequency component which you are giving from the noise, that is the input now. All remaining frequency components will be died out indirectly. Only this is the frequency component which is what is given. Then what is the input? That is in the order of microvolt peak to peak, or hundreds of microvolt, or tens of microvolt from noise, thermal noise. Therefore, you will be getting output also microvolt peak to peak. We don't want microvolt peak to peak. We want volts peak to peak. Then I want more positive feedback, or I want more loop gain. If I have more loop gain, you know what will happen? If A beta, therefore practically if you take practically because your oscillator output, then if you ask me what is your peak to peak, the peak to peak will be in the order of microvolt. Therefore microvolt peak to peak due to noise input, due to noise input, because your noise will be in the order of microvolt peak to peak. That's why practically your A beta, mod A beta will be slightly greater than 1, but nearer to 1, not like 2, 3. When I say mod A beta slightly greater than 1 means 1.1, that is what it is. If you take practically your mod A beta slightly greater than 1, then if you ask me your oscillator output, right, I'm ignoring the first part. Once you get F0, right, once you get F0, slowly your oscillations will get overdamped oscillations. Why you get overdamped oscillations? Because your mod A beta greater than 1. If your mod A beta is greater than 1, you will get mod A beta greater than 1, you will get overdamped oscillations. But remember, your overdamped oscillations will be limited by your two things: amplifier non-linearity, because I told you, right, amplifier is having non-linear. If amplifier is non-linear, right, when I said this is what your V0 and then Vi, right, it is something like this. If amplifier is non-linear, we are not getting the same gain, we are not getting the same gain at higher voltages. We are not getting the same gain at higher voltages. There is a gain loss. This is nothing but your gain loss at higher voltages. There is a gain loss at higher voltage. People say 1 dB compression point. So many things are there, or that may be. People use them in RF, or that may be. There is a gain loss at higher voltages due to non-linearity. Because if you go lower voltage, it is linear and it is tracking too, and the gain, whatever you are getting, the same gain is expected. But now at lower voltages, whatever you are having the gain, the same gain is not expected or not coming at higher voltages. Therefore your gain will be limited. Even though you are starting with mod A beta, which is nothing but slightly greater than 1, that is applicable for lower sine wave peak to peak. But as the output signal peak to peak is increasing, the gain of your open loop amplifier due to non-linearity, that will be limited, or that will be decreased at higher voltages. You know, the gain will be close to, or the total loop gain will be close to equal to 1. Indirectly, noise is helpful for the oscillations. Indirectly, the non-linearity of your amplifier is also helpful to get oscillations, right? To get sustained oscillations for higher voltages. Then you know, practically it will be going to what? It will be oscillating in between your rail to rail. Or I can explain one more thing, one more practical point. See, it is limited. It is defined with plus VCC and then minus VCC. If it is defined with plus VCC and then minus VCC or op-amp, we cannot go more than VCC, we cannot go below minus VCC. Definitely it will be in between plus VCC to minus VCC. Let us say, due to at higher voltage also, gain is decreased, but it is not decreased much, but still it is greater than 1. Let us say it will be limited, but let us say it is still, your loop gain is greater than 1.01. Your sine wave is trying to increase, but now the sine wave will be limited by your rail to rail of your op-amp output. Let us say, then definitely it will be in between rail to rail, then it will be always oscillating, then you will get sinusoidal oscillations, sustained oscillations practically. Remember, that's why practically the mod A beta will be slightly greater than 1, not very much greater than 1, slightly greater than 1, because whatever noise which you are getting through temperature, that noise will be in the order of microvolt peak to peak. That will be restored if loop gain is equal to 1. Then that is in the order of microvolt. That is not sufficient. We want to boost it. Therefore, the loop gain should be greater than 1. If loop gain is greater than 1, then slowly it is what is having over damped oscillations. But remember, it is limited by your non-linearity of your amplifier and your amplifier output rail to rail. Therefore, both of them will limit your oscillations output in a given fixed peak to peak. Then you will get always sustained oscillations. I hope everybody understood. Okay, take it. Maybe one more point. Let us say temperature is increasing. If temperature increases, what will happen? Now, at this frequency, which is 1 kHz, now we will not get 180 degree phase shift by beta network. That 1 kHz will be died out because it is not satisfying total loop gain or total loop phase shift. Then, but noise is continuous, right? That frequency which is nothing but 1 kHz will be died out. Now that will be slowly died out. Then one more different new frequency component will be picked up. It will pick up a new frequency component. At new frequency component, because continuously noise is present, thermal noise is present. Now that thermal noise, which is the input, that it will pick up a new frequency component where the total loop phase shift is 0 degrees. Then remaining frequency components will be died out. Again, that will be restored, and that will be coming, that will be giving you a new frequency of oscillations. I hope this is clear, right? Remember, only the frequency component which has total loop phase shift is equal to 0 degrees, that is what is having positive feedback, will be restored. Remaining all frequency components will be died out. If temperature changes, phase shift changes, that frequency of oscillations will be changing. It will be frequency of oscillations will be died out. New frequency component will be picked up from your noise, then that will be restored, and that will be gained, and that will be oscillated, or that will be sustained. Okay, I hope this is clear. Okay, done. This is very important. That's why when you solve some oscillator problems, practically people consider mod A beta slightly greater than 1. Okay, not equal to 1. But under steady state, where you want to get full output sine wave peak to peak, that will be having almost A beta will be 1. Okay, take it. See, this is what is completely qualitative part. All these things are useful if somebody is asking in the interview questions. All individual points are known to everyone, but correlating, combining, and then getting the summary or observation, that is what is very important, which you will not see in any book. That I am sure. I'll come in a minute, try to write. Done? Now we can go to almost 2.5 sessions are taken by only RC phase shift oscillator. But now from now onwards, you see how many sessions will be taken by each oscillator. Okay, it will be faster because I explained how noise is input. I explained why practically loop gain is slightly greater than 1. I explained what is frequency stability. I explained why the range of RC phase shift oscillator is less. That is because of bandwidth limitation of your open loop amplifier. So many points we got to know. Now next time onwards, we will know all the reasons. Then we can go straight forward. Remember, we can use common emitter amplifier also, or we can use common source amplifier also to get gain of minus 29. Okay, but that will have some loading effect and all, and source effect. Therefore, means the resistor whatever you have from final RC circuit, that will be in parallel to the input impedance of your CE amplifier. Therefore, that input impedance will be in parallel to R, then the resonant frequency should be calculated with respect to that. Therefore, all those things will give you a little complex equations, but you will get it. It's not a problem, but it's better to go ahead with Opamp. Opamp will give you simply minus R2 by R1, and assuming the output impedance of Opamp can be neglected with respect to the resistor, which is what is used in the RC phase shift oscillator. Okay, I hope this is done, right? Okay, now second circuit. Now again, see, tell me, I'll tell you the motivation for the second circuit. Okay, the motivation for the second circuit is, tell me, in the RC phase shift oscillator, how many resistors and how many capacitors are used? 3 resistors and 3 capacitors are used, right? And 3 resistors are used, therefore more power dissipation. More power dissipation, more beta network loss. More beta network loss, we are expecting more open loop gain, which is 29. I'm speaking about magnitude. Therefore, we need more gain, which is 29, because of the loss by beta network at resonant frequency, which is 1 by 29. If you can decrease number of resistors, and if you can decrease number of resistors, therefore we can decrease the loss by beta network. If you can decrease loss by beta network, then we can have less gain requirement from your open loop system. If you can have less gain requirement from your open loop system, then your bandwidth can be increased for the same for the lesser gain. Then we get more frequency range of oscillations, because our figure of merit, number 1, frequency range of oscillations, number 2, frequency stability. Therefore, how to improve frequency range? We need gain requirement, open loop gain requirement lesser than 29. Therefore, we need lesser loss by beta network. Therefore, we need less number of resistors. If you have less number of resistors, lesser loss, lesser open loop gain requirement, more bandwidth, because gain into bandwidth is constant. If gain requirement is lesser, you'll get more bandwidth in the sense it can support more frequency range of oscillations. That is the motivation. Therefore, some guy took, this is what your open loop amplifier, the block diagram, this is what your open loop amplifier A, and now the beta network is given like this. The beta network is nothing but series RC and parallel RC. It is not RC phase shift oscillator, it is simply a beta network having 2 resistors and then 2 capacitors. That's it. Therefore, if you have 2 resistors only, the loss is less when you compare with RC phase shift oscillator. In the case of RC phase shift oscillator, 3 resistors, therefore more loss. Now we have only 2 resistors. I'm just explaining proportionally with respect to number of resistors. Therefore, this is what it is. Now, this is what your beta network. This is what is the beta network. Okay. Then output of beta network is given to input of the amplifier. Right. Therefore, this is beta network. Therefore, who is dictating your resonant frequency? Beta network is the one which is what is dictating your resonant frequency. Now, we need to calculate the transfer function of beta network. Once you know the transfer function of beta network, then we will try to get the beta without J term, then that will give you resonant frequency, and then as it is, whatever we did in the case of RC phase shift oscillator, similarly we have to do. But in the case of RC phase shift oscillator, 3 RC networks, but here series RC, parallel RC, and an amplifier. Let's see what is the beta network phase shift at resonant frequency. Then we can ask for the phase shift requirement from your open loop amplifier, and let's calculate what is the gain by beta network at resonant frequency. We can ask for the gain from open loop amplifier. Definitely the gain of beta network will be, or the loss by beta network will be lesser than RC phase shift oscillator. No doubt about it, because of less number of resistors, less loss. Okay. Now let's see what is beta. To find beta. Right. Therefore, what is your beta network? Your beta network is nothing but this is simply series RC, then parallel RC. This is what is your parallel RC. Okay. This is R, this is C, and then R, and then C. Let me take it as this is V0, and this is what is your VI. Okay. Therefore, can I consider this as series RC as Z1 and parallel RC as Z2, if I write like this, therefore equivalently can I write this as, this is Z1 and this is Z2. Okay, now this is what is ground, now this is what your V0 and this is what your Vi. Simple, right? Then it is simply voltage divider network. But we should know what is Z1, we should know what is Z2. You can write in S domain, later on we can substitute and then we can get phase shift or magnitude, whatever you want. Okay, now let's see. Therefore what is Z1? Your Z1 is nothing but your Z1 where Z1 is nothing but what? Series RC, right? R plus 1 by SC, which is nothing but, if you take SC common, then 1 plus SCR. Now what is Z2? Z2 is nothing but, these two are in parallel, therefore R into 1 by SC divided by R plus 1 by SC. If you do that, SC will be cancelled, R divided by 1 plus SCR. Therefore you know what is Z1 and you know what is Z2, right? Therefore if you know that, then what is beta? Therefore beta is equal to what? V0 by Vi. Therefore what is V0 by Vi? Voltage divider network. Z2 divided by Z1 plus Z2. You substitute Z2, you know already, substitute Z1 and then find beta in terms of S, then substitute S is equal to J omega and separate real part and then imaginary part. Then let's see the condition for making beta independent of J, that will give you resonant frequency, and at that frequency that will give you the loss by beta network, then problem is over. Okay, then I'll after completing everything, I'll name what is this oscillator. It is not RC phase shift oscillator, it is some oscillator, but I'll tell you why it is that oscillator. Okay, you take it and then try to substitute. I'll wait for 2 minutes. The session is over, maybe you can continue. Therefore you substitute Z1 and then Z2 here and then try to get beta and then tell me what is beta in terms of J, then we will see the observation part. Okay, try to do. Take it. Beta greater than 1. Okay, fine. I'll stop in this session. You just continue and then try to get, anyway I'll derive it in the next session. Okay, thank you.